Okay guys, in this video we're just going to go over a few of the questions from exam 2 for the most missed questions. So we're going to start off with the sample variance is computed by dividing the sum of squares, or SS, by n minus 1. The sample variance will always be blank than the population variance. So to start this out, let's talk about the differences between the sample variance and the population variance. So remember, for the sample variance, this is our sum of squares divided by n. And for the that's the population, my bad. We've got this. And for the sample, our variance is computed with the sum of squares divided by n minus 1. So if, for example, we do the sum of squares being 20 and our sample size being 5, then when we compute the population, this would be 20 divided by 5, or 4. Whereas if we do the sample, this would be 20 divided by 5 minus 1, or 20 divided by 4, which would happen to be 5. So notice that the population is smaller than the sample. Now, since we are talking about the relationship between the sample and the population, then we're going to say that the sample is always bigger or greater than, because we're actually going this direction. So notice my sign is eating my sample, which means my sample is bigger. So my sample is always greater than my population variance. Okay, so this one says the box plot below depicts the median number of hours a population of n equal 12 students reported studying for their first exam with a class. Which statements are true? We want to select all of the correct statements. So starting off, it says the highest score in the distribution is 7. So if we come across here, it looks like that is actually true. The highest score is 7. So that works out. Then it says the interquartile range is 5. So remember, when we do the interquartile range, that's that IQR. And that is our Q3 minus our Q1. And when we're looking at this, the top of our box, that's going to be our Q3. And the bottom of our box is going to be our Q1. And I know it's a little bit hard to read, and I didn't do a very straight line, but this is about 6.5 minus 2.5, which would give us 4. And that is not 5, so this is not a correct answer. It says the lowest score in the distribution is 1. Remember, the lowest score is the bottom of our whisker here, and that is indeed 1, so that's good. And the median is 5. Remember, the median is here at our center. This is our median, and if we come across, that's pointing straight at 5, so that is correct as well. So when we answer this one, we would have said this answer, and this answer were both correct, since we are all 3 correct, since we were selecting everything that was correct for that. Okay, so now on the next one, we're going to do what we call our 5-point summary, and we're also going to find that interquartile range. And then, in addition, we're going to do our variance and standard deviation for this set of data. So we're going to start off, and this is a sample, by the way, so we did say sample scores, so we are working with that. So what we're going to do our 5-point summary is we are going to put these numbers in order. So if we put them in order, we have 1, 1, 2, 3, 4, 6, 7, 8, and 9. The easiest 2 that we can do is the low, which is going to be the number 1, and the high, which is going to be 9. So now we need to do our quartiles. Remember, when we always start with Q2, which is our center number. So we count how many numbers we have. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9. Since we have 9 numbers, our median, or our Q2, is just going to be our center number, which happens to be the number 4. So this is our Q2. Now when we find our Q1, we want to look at numbers over here. We want to find the middle. Since there are 4 numbers to the left of that, we're going to take the center or the median of these two, or the average, I'm so sorry, we're going to add 1 plus 2 divided by 2. So that's going to give us 3 over 2, or 1.5. So our Q1 is 1.5. I'm going to do the same thing here to the right-hand side. Since there are 4 numbers, again, we're going to take those center 2, 7, and 8. We're going to add them together and divide by 2. We're just averaging those numbers. That becomes 15 over 2, or 7.5. So there's our Q3. So then to find our IQR, remember we just do our Q3 minus our Q1. So this is 7.5 minus 1.5, or 6. Okay, so now the hardest part is to do our last two, which is our sample variance and our sample standard deviation. So remember to do this. We've got a couple little formulas we need to remember. So we need our sum of squares, which is the summation of our x's squared minus the summation of x, and then we square it and divide it by n. Once we find that, we can do our variance, which is our sum of squares divided by n minus 1. And then after that, s is just equal to the square root of s squared. So we'll find our deviation that way. So the way I like to do all of these when I'm doing these is I want to do a chart really quick. I have my x's here, I have my x squareds, so just going to list all my x's. Since I've already got them in order, I'm just going to keep them in order. So 1, 1, 2, 3, 4, 6, 7, 8, and 9. And we're going to sum all of those numbers up. So the sum of your x's is going to be equal to 41. Okay, and then we're going to come over here and we're going to take each one of these and square them. So we've got 1, 1, 4, 9, 16, 36, 49, 64, and 81. And again, we're going to sum those up. So this is the sum of our x's squared. And that is going to add up to 261. So now we're going to come up here and do our SS. So SS equals 261 minus 41 squared divided by 9. Remember, our n is 9. We had 9 pieces of data. And when we do all of that good math there, this is going to be 261 minus 186.778. That's going to end up being 74.222. So then to find our s squared, we're going to take 74.222 and we're going to divide that by 9 minus 1. And that is going to end up giving us 9.28. And then to take that, I'm going to take the square root of 9.28, and that's going to give us the 3.05. So our variance is 9.28, and our standard deviation is 3.05. So finding the standard deviation and the variance is quite a little bit of work, especially when we're doing it by hand. But if you'll do your chart like I did here, then it makes it a lot easier to go through that process, as well as being able to plug that information into our formulas. Okay, so on this one, again, we're going to compute the mean and the standard deviation based on this graph. So the first thing we kind of want to do is go ahead and write out our points. So this is going to be 2 and then 3. We have 1, 2. And it's not supposed to be 2. That would be a 1, 3. And then notice that on our 6 column, we have 5 6s. So 1, 2, 3, 4, 5. And then we have 1, 7. And we have 3 8s. So 1, 2, 3. And put my commas in there. We have 1, 9. And again, 3 10s. All right, so now what we're going to do is we're going to find our mean. Well, let's go ahead and start our standard deviation. Since we are going to have to do that anyway, I'm going to do it out here since I've got a little bit more room as far as my numbers here. So this is going to be x, this is going to be x squared. So we have 2, 3, 1, 2, 3, 4, 5. Then we have 7, 8, 8, 8, 9, and then 3 10s. And when we add all of that goodness together, we are going to get, hold on, we're going to get 105. So this is the summation of our x's is equal to 105. So to find our mean, remember when we're finding our mean, this is going, and this is a population, so it's going to be our mu is equal to the sum of our x's divided by n. So this is going to be 105 divided by, and then how many n's we have, or how many data points we have. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 data points. So if we do 105 divided by 15, we get 7. So there's our mean. And now to do our standard deviation, we need to do all of our squares and add those up. So we have 4, 9, we have 36 5 times, 3, 4, 5, 7 squared is 49. We have 64, 64, 64, 9, oops, nope, how about 81, there we go, and then 100 3 times there. So now we just need to add that column up. Okay, hold on. And I did this a little kind of cheating here. Those 36s, that's 180. The 364s right here, that's going to be 192. And this is going to be 300. So what I need to add together is the 4, 9, 180, 49, 162, 81, and 300. So if we add up all of those good numbers together, okay, so the summation of our x's squared is equal to 814. So now again, remember our SS, that's going to be the summation of our x's squared minus the summation of our x's and then squared divided by n. So start off with that. So we're going to have 814 minus 105 squared divided by 15. So 105 squared divided by 15. We have 814 minus 735. So 14 minus 735, and that gives us 79. So to find our variance, we're going to do 79 divided by 15. That's going to give us 5.2, oops, let's try that again, 2667, and then to find our standard deviation, we're going to take the square root of 5.2667. And we should get 2.29. Might be off a little bit on that one, but that's our process. So the biggest thing when you're doing, again, the standard deviation is to pay attention to whether it says the population or the sample, because if you do the population, remember we divide by n, but if you do the sample and we divide, when we're doing our variance and our variance, we divide by n minus 1. The sum of squares formula doesn't change for either one of them. That stays the same whether it's population or sample. What changes is your actual variance. Okay, so let's look at the next problem that says, using our information above, determine whether or not 10 is an extreme score, and the same thing for 2. So if you remember, our mean was 7. So our mean was 7, and our standard deviation was 2.29. So what we're going to do is find the z-score. So remember, the z-score is the score minus the mean divided by the standard deviation. So this would be 10 minus 7 over 2.29. And the closer a number is to, your z-score is to 2, the more extreme it is. The closer it is to 0, the less extreme it is. So if we do this, we get 10 minus 7 is going to give us 3 divided by 2.29. And we get, 3 divided by 2.29. I got to actually do it right in my calculator. We get 1.31, which I know it's greater than 1 standard deviation, but it's still within reason. It would not be considered an extreme. It would be more of a typical score. So let's do the same thing for this one. We're going to do it with 2. So again, we're still using those same values. So we're going to do our z-score here, and it's going to be 2 minus 7 over 2.29. So 2 minus 7 is going to give us negative 5 over 2.29. So if we divide that by 2.29, we get negative 2.18. And since this is bigger than 2, and I'm not even really concerning myself so much about the negative, I'm just thinking of the thing, thinking of the fact that it is 2 standard deviations away from my mean. This would be considered an extreme score. So when it's talking about justifying your response here, I'm really wanting you to understand that for something to be an extreme score, it needs to be either bigger than 2 or smaller than negative 2. That's 2 standard deviations away from my mean. And if you think about our percentages, when we think about how things work, remember that 68% of your data lies within 1 standard deviation. And then 95% of your data lies within 2 standard deviations. That means that only 5% of your data lies outside of 2 standard deviations away from your mean. So when you get a number that's bigger than 2 or smaller than negative 2, that means that it's in that 5% area on either side of your bell-shaped graph. So it would be considered an extreme value. Okay. All right, so it says consider the population with a score of x equal to 15 and a z-score of 1.5, a positive 1.5. What does this score indicate about the location of 15? So first off, it is a positive score, which means that it is above the mean. Okay, negatives mean they are below the mean. Positives mean they are above. So automatically we get to nix out this answer right here because it says below the mean and we know our value is above, and we get to X out this one because it also says below and we are above. So then remember that this is the number of standard deviations away from the mean. Okay, we already know it's going to be above it, but we're talking about how far away. So if we read this first one, a score of x equal to 15 is 1.5 standard deviations above the mean. And that's what we're talking about, standard deviations away from the mean. So that means that this would be our answer right here. Okay? And then notice that this is talking about the mean units away from the standard deviation. We never talk about that. We always talk about standard deviations away from our mean. For a population standard deviation of 5, what is the z-score corresponding that is 9 points above the mean? So I want you to think about this. Z equals x minus the mean divided by the standard deviation. This whole statement right here, this is the difference, because that's subtraction, between a score and the mean. So if my score is 9 points above the mean, then that means that the top of my fraction here is 9. Okay, that means that when I subtract whatever my score is from the mean, I get a positive 9. It's positive because it's above. And then I'm going to divide that by 5. And 9 divided by 5 is going to get me a positive 1.80. So anytime it talks about something being, that a score being above or below the mean by a certain amount, then that's just the top of your z-score. Basically, it's telling you the top number of that z-score, so you're not having to do the subtraction to figure that out. So in this case, the second one is going to be our answer for this particular problem. Okay, so z-scores are primarily useful with regard to inferential statistics because they offer a tool by which to determine whether an individual is different from a sample, a distribution score is symmetrically shaped, a distribution score is standardized, or a sample is notably different from the population. So we're going to nix this middle two. We're not talking about the symmetric shape. We're already assumed that it was symmetric. And we're standardizing, the z-score actually is the standardization. So we're not going to talk about this one. So we're either talking about this first one where we're talking about an individual different from a sample, or a sample different from a population. But we are specifically talking about inferential statistics in this particular question. And remember, inferential statistics is all about being able to take a sample, determine if it's different from or if I do some type of treatment and it's different, does it have a result that's different from my population, and then being able to push that back to the population. So I don't really care about an individual person. I care about a sample of people because I am talking about inferential statistics, which is to take a sample, do something, and then try to push that back to the population and say, yes, this has a difference for the population, so we're going to expand this thought. So this is going to be this last answer here where we're talking about sample and population. And again, we're getting that from the fact that we're talking about inferential statistics, not just z-scores, but inferential statistics. Okay. So last week, Tim obtained a score of 54 on his math exam with a mean of 60 and a standard deviation of 8. He scored a 49 on his English exam with a mean of 55 and a standard deviation of 3. He scored a 31 on his psychology exam with a mean of 37 and a standard deviation of 4. For which class did Tim expect the worst grade? So what we're looking for is what we're gonna do to do this is we're gonna find the z-score, and we do have to find the z-score since each one of these tests has a different mean and a different standard deviation. We can't just compare the grades and look and say, well, he made a 31 on his psychology exam, so obviously that was the worst exam. But if I look at here, the mean was only a 37. So we have to look at both the mean and the standard deviation for each test. So that means we're gonna find the z-score for each one of these. So we're gonna start with math. Again, remember that the z-score is x minus the mean divided by the standard deviation. So for the math, that's going to be 54 minus 60 divided by 8. So this is going to be negative 6 over 8, or in z-score terms, negative 0.75. Remember, when we talk about z-scores, if we do have to round, we always round to 2 decimal places. So then we're going to look at English. So English's z-score, he made a 49 on the exam. The mean was a 55. The standard deviation was 3. So this is going to be negative 6 over 3, which ends up being -2. So obviously he did worse on his English exam than he did on his math exam, because look how much lower his z-score was from the math exam. So let's look at the psychology exam. Let's see how he did there. So Tim made a 31. The class average was a 37 divided by a standard deviation of 4. So this is going to be -6/4. And -6 divided by 4 is going to be -1.5. So we can see here that the English exam, it has the lowest z-score at -2, so he did the worst on that lowest z-score. And it would be very easy to assume that he did the same on all of them, because you'll notice that when we did that subtraction on each one of these, it came out to -6 on the numerator. He scored 6 points below the average on every single one of them, but because of that standard deviation was different, it changed our z-scores. Okay, and that's common because we are looking at not just how high or how low he scored from the mean, but how is that compared to the rest of the class? How did the rest of the class score as well? So always having to make sure we take into account that standard deviation. Okay, which of the statements below are true regarding standardized distributions? And we are going to again select all that are correct. So it says standard distributions are used to make otherwise dissimilar distributions comparable. What that basically means is exactly what we just did on the last problem. Being able to compare an English test and a math test and a psychology class that all have different means and different standard deviations, or being able to compare the SATs with the ACTs that have completely different scale measurements. You know, the ACT only goes up to, I think, 60, whereas the SAT goes up to 1600. So being able to compare those things. So that is true. That is what we do with our standardized distributions. It says the z-score distribution on an exam of a standard distribution. So yes. The values for the mean and standard deviation for standardized distributions matches those values obtained for the original distribution. That is not true. Standardized distributions consist of scores that have been transformed to create predetermined values for the mean and standard deviation. Remember, for your z-score, your mean on a z-score is always 0. Okay? And your standard deviation on a z-score is always 1. So that is a predetermined value. So this is also true. So they're just kind of basically, again, listing all the things that are true about a standard distribution. And what we're really talking about here when we talk about this is just think about those z-scores and what they do. That's what we're looking at. Okay, this next one is very similar to this, not the last problem we did, but the problem before that. We have 3 people, Sue, Bob, and Mary, and they all took the same test, and we're trying to determine who has the best score, who had the highest score. So for the exam, I had a mean of 74 and a standard deviation of 8. It says Mary scored an 80. Okay, so let's look at Mary, and let's find out Mary's z-score. So z equals 80 minus 74 over 8. So if we do that math, 80 minus 74, that's going to be 6 over 8, and that is going to give her a 0.75. Now Bob, that just told us Bob made a 1.5 on his z-score. So we can obviously see that Mary did not do better than Bob. But let's look at Sue. Now, Sue scored 10 points above the mean. And remember that problem we did earlier. That means that the numerator is going to be 10. And we're going to divide by our standard deviation of 8. And 10 divided by 8 gives us 1.25. So Sue also did not do better than Bob. And Bob ended up being the winner of who did the best on that exam. Okay, I'm going to continue doing a couple more examples in the next video.